So, hello again to you all. This is lecture 2 in the course on grazing incidence small angle scattering. This lecture is about transmission small angle scattering, and my name's Chris Garvey. Just a very brief outline of a very brief talk. In this talk, I'm going to define the technique of small angle scattering and its measurement, so what we measure and how we measure it. I'm going to talk also in terms of the kinds of samples that we use for small angle scattering and how they're different from both reflectivity samples and grazing incidence. Not so different. There's not so much difference between reflectivity and grazing incidence samples. I'm going to also talk about the instrumentation that we use to measure transmission small angle scattering, and how we analyze small angle scattering is also important. I'd note at this point that there's really quite a big difference between the analysis of small angle scattering and grazing incidence small angle scattering. Grazing incidence small angle scattering is sort of a hybrid technique which takes aspects of reflectivity and transmission small angle scattering, both conceptually in terms of the instrumentation and also in terms of the analysis. So here's a slide where I introduce 3 techniques. I have a sample and a measurement geometry. If we think of specular reflectivity as a one-dimensional probe of structure, these grazing incidence off specular techniques look at 2-dimensional structure, and what I'm going to talk about today, transmission small angle scattering, is a reconstruction of largely 3-dimensional structure. So in the case of specular reflectivity, the sample is a thin, flat film, and quite often that's something deposited on a solid substrate or a support. We measure the intensity as a function of angle, so there's a beam of X-rays or neutrons which have an incident angle on the sample, and we have a detector that can be an area detector or a point detector which measures at the same angle, the reflected beam. And we look at that, the relative intensity of that reflected beam as a function of this angle, or how it's normally expressed in terms of the wave vector q, and this is the reflectivity. What we're probing here is the composition in a direction normal to the surface, so the depth profile. And what we have here is different thickness layers, and you can see that as the thickness of the layer increases, the fringes get closer together. And to a first good approximation, the period of those fringes is a good indication of the layer thickness for simple layers. The data analysis in this case is usually done by comparing a calculated profile with an SLD model. And from that we get information about the composition and the thickness of layers. But Marite will talk about that in a lot more detail than just this slide. We'll have a separate lecture on this, but I'll just talk about this briefly. So the samples for specular reflectivity and grazing incidence are fairly similar. We have an incoming beam, and in this case the angle of the incoming beam is fixed, and we have an area detector at the side. And so we will probably measure on a point the reflected beam, but we'll have all this other information on the area detector around the reflected beam. So that's the grazing incidence and off-specular signal. What the experiment is probing is in-plane organization. So organization in the thin film or the surface. That's why I call it a 2-ish dimensional technique. What I'm going to talk today about is 3-dimensional structure, reconstructing 3-dimensional structure from this very simple experiment where we collimate to find the direction of a beam of X-rays, neutron or light. It goes through a sample, so some of it's transmitted. But what we're really interested in here is the scattered beam. And we measure that as a function of angle, usually on an area detector. But we can, some of the older instruments, scan across or with a linear detector. The data analysis of this technique is a lot more flexible than either of these two other techniques. We can do the same trick that we do with the specular reflectivity. We calculate the scattering due to a structural model and compare that with what we actually measure. Or there's more direct methods of getting structure from the scattering curve, which I'll talk about later. So here it is in all its simplicity, the small angle scattering experiment. So we have a beam which is collimated. And all that means is that we define the scattering angle very well, that most of these neutrons, X-rays, or light are going in the same direction. And they interact with the sample and they're scattered, they spread out. And we measure the intensity as a function of angle. And without worrying too much about what the analysis, what one is in fact doing is producing a image. So in this case, the sample is, and this is actually data from red blood cells, and one gets this scattering curve. And from the data analysis, one can look at the organization of hemoglobin molecules, which make up most of these red blood cells that form this pattern, inside the cells. And so one takes a reciprocal space image and turns it into a real space model. So how do we get from what we measure, which is the intensity as a function of the scattering angle, to the structure? And what we need to first do is, independent of the instrument, measure a property of the sample, which is the absolute scattering cross-section of the sample. The first thing we need to do is normalize the incident flux of neutrons or X-rays on the sample. So we know how many hit, then we can describe the probability of them being scattered through a particular angle. We need to know how many, if we're counting on a pixelated detector, how big the detector is, how big the angle subtended by a solid angle subtended by a pixel is. We need to know how efficient the detector is, because we use different kinds of radiation and different kinds of detectors. We want an absolute number. For the time of flight technique, this is also a function of wavelength of the neutrons. We need to know the sample transmission, and this comes back to an accounting for the neutrons or X-rays that hit the sample, whether they're absorbed, whether they go through, whether they're transmitted, or whether they're most importantly scattered. We need to take account of the volume of sample illuminated by the X-ray or neutron beam. The more sample we have, of course, the more scattering we have. This could be as simple as the sample, the beam diameter, which illuminates more or less sample depending on how big it is, or the sample thickness. The important thing of the sample thickness is if the cross-section is too high, the probability of a scattering event as we go through the sample becomes much larger. If we make the sample thicker, the neutron or X-ray can be scattered multiple times. And in general, we don't account for that in the analysis. That's actually an important difference between grazing incident scattering and this transmission small angle scattering. And the final information that we're after is the probability of a neutron being scattered through a particular solid angle. So if we think of the features on a scattering curve as two basic categories, there's diffraction features, which are the result of some well-defined correlation length, and the position of that allows you to measure some characteristic distances. In lipid membranes and self-assembled systems, one can use this to put together some information about the space group of the periodic structure, and there's quite a nice review there. And there's more diffuse scattering, which is not so well defined. It's usually maybe a badly defined peak. Simple decay is characterized by different slopes. In the case of small angle scattering, both of these can be analysed quite easily. In the case of grazing incidence measurements, it's the diffraction which really gives you the most information. So just some broad comments on data analysis of small angle scattering. One can analyse the slopes of the log-log plot, the log intensity versus log Q plot. That gives you some idea of the shape of the scattering objects. There's some model-dependent laws about scattered intensity. So the Poe invariant is the total scattered intensity, and that gives you information about the amount of interface between phases. The Gunier law gives you information about the size. There's direct transform methods, which I'm not going to talk about so much. And of course, there's modeling. You can just calculate what the scattering due to some sort of core shell structure is and compare it to what you've got. So that's an overview of the small angle scattering technique. Just keep this in mind when I come to give the lecture on grazing incidence. Thanks so much for your attention, and if you have any questions, you can email me.